on this computer. All right, so share screen, share. So welcome everybody. The lesson of today will involve the solution to the exercises that I had proposed last time, one after the other, and also maybe I will manage to explain a little bit or to show you an example on how to use smart pointers on the tree. So we will do the exercises one after the next. Let's come to the first. The first exercise was asking you to load a list of integers into a structure at your choice. You could do a vector, or I think I said a vector. Yes, a vector, because the vector supports sorting. And by opening a stream and then printing out these values one after the next. So let me close the window because it's, I don't know, all possible sound outside, or is it can you hear this? No? Or maybe the exercise was, I hope, quite easy. Please open the microphone because I'm not gonna hear what you say. Okay, guys, at home. I'm not gonna read the chat if you have questions. So it's a good habit that I have, the one of, instead of bringing together with me the expressions of templates, of types of templates that look ugly, when I have something that I don't need explicitly to see the arguments of the templates, I just rename it. So let's define a vector, std vector of int. This is not necessary. At the same time, it makes, I believe, the code easier to read. All right. I mean, clearly you could replace any instance of int vector with the std vector of int. Now, why std? Okay, now that's something that I didn't tell you, and let me introduce the game of the namespaces. Once you have a large C++ program, it's almost unavoidable that two modules declare a function or a class. Can you, whoever is speaking, can you mute himself? Unless you have something to say. It's quite common that you have two classes in two different libraries that might have the same name, right? And this is a pain. Let's say I have a library, my library, where I declare a function A and I call it F. I have another library, I have another function, and I call it F. Now the problem is, like, which of the two F's am I calling? A solution to this is to define a so-called namespace. Namespace is like that. Where you do something, right? And so basically all these two classes are declared inside this namespace. If outside of the namespace I want to declare an instance of class A, I will have to do my namespace A. Okay, guys? Of course, namespaces can be nested. So here I could have another namespace. I have problem with the touchpad, which now I will disable forever. Right? In this case, if I want to declare an object of class A, I will have to resolve the namespace. So I will have to say my namespace, column, column, my nested namespace is like directories. Right? Clear? Like browsing directories. So you could enclose your library into a namespace. You can also have a namespace. You can also add things to this namespace in a different file. You can just say namespace and then you start adding things. Right? You could have two files. Maybe there would be another file. And you could add a class C. Right? Clear? And that's the way. So given that the live, you can imagine that many programs use the word list, right? In order to avoid mess, in order to refer to the list of the STL, we call it standard list, okay? Now, it might be that during your program or whatever in your main file, you don't have these namespace clashes. So what I normally do in order to avoid every time to saying std column column, so resolving the namespace manually, I just write once using namespace this, which basically brings everything of that namespace into your current namespace. This is the namespace resolve. Is that clear to the ones in the class? Yes. All right. Now, given that I use the namespace, I could just like say using int vector equals vector of int, right? And then interesting, I include the header file algorithm that contains the sort. How did you find that the sort lives into the header file algorithm? If you ask Google, Google is going to tell you where the sort is of a vector. What we do, we say, please program crash if the number of arguments of the command line is smaller than 1. Okay. In this way, basically, the program doesn't crash if you don't feed it. Actually, it should be 2, because the first name, the first token of the command line is always the program name. Then we're gonna get the second argument, which is basically the input of we write, like we will write the int sort file name, and that's gonna be the file name. We open the stream. We have to declare a vector that is gonna contain the values that are gonna be sorted, and then we have to read the file until it's over. And we use the loop that we have seen it in the slides last time. So we just like check on the input stream. So like if you do try to convert an input stream or a stream to a Boolean, it's gonna return you true if the stream is good. An alternative would be to use the method good, while is.good, that is a method defined in the class iOS. And then to read a value, we need to have a variable where to read it in, because the greater operator defined on the streams is overloaded by the type it is gonna read. So we have to declare exactly an int if we want to read an int. So we read this integer into the variable I, and then in the action of reading the stream, we might have encountered the end of file. Okay, so in order to avoid of reading the last value as wrong, we check after reading whether this input stream is still good. And then at this point, we can call the pushback function of the vector, passing it the element I. Okay, and then we can sort. Remember what I said about the sort. Sort requires a beginning and end. I mean, at least this synopsis of the function. It's not that I can teach you libraries, but the standard sort takes a begin, takes an end, and in theory takes a comparison operator. But in this case, if you don't define the comparison operator, the sort is gonna use the standard comparison operator, which is the A minus B. So the A smaller than B. It tries to use the smaller operator, right? And then the last thing that we do, like in a more modern C++ syntax, is to loop through the values by using the funky auto thing. So declare a variable for each value into the array. Give me the reference that I can write in. Actually, I could write here const because I'm not modifying the value in the action of printing it, so it's more conservative. And then I print all the values on the standard output, which is a string, no, one after the other. I put an end line, just like to go to the next line after. Was this clear, guys? For you at home, do you have questions? Open the microphone. I'm not reading the chat. If you have questions. No. Okay. Then if you want to test it. RP05 thing. Solution. No. Source. In this case, I put the CMake there. mkdir build, or let's build on the top level directory. Build. Well. Source. Make. So of course I'm building all the files now, but now I'm gonna have here int sort to test int sort. I will launch int sort, and then I have to pass to this file, to this program, a list of integers, right? That I should have in a folder that I've given you. It's called test data. Test data. Int test data. And this is the integers. Let's see how int test data is. Test data, int test data. This is a bunch less, not a less. Less is equal to cat, simply allows you to go up and down a file, but in this case there's no up and down to go because the file is more than a page. So here we find all the integers that are unsorted. In the output, on the standard output, we have found the same integers, just sorted. Questions on that? Clear? Questions on Linux? I mean, I'm just calling the programs as we have always done, and now we introduce the program less that serves to browse a file up and down. I could also use the cat instead of less. That just prints, right? Clear? Very good. No questions on this exercise, I imagine. And let's move to the next, the more like meaty one, a little bit more juicy, which was loading points consisting of, you can look at the slides for those at home. The idea is that you have a file where in each line you have an integer and 3 coordinates. X, Y, Z. Each of these rows should be loaded in an appropriate structure, which presumably will contain an integer and 3 coordinates, or an integer and, for instance, a vector f. If it is a struct, you can compose it, right? And then would load this data with creating, I think, a list over a vector. I don't remember. It was a vector. Creating a vector of these things. One per line, storing the content of the file, and then it was prompting the user the possibility of selecting, and we want to sort it by index, by the first row, the second row, the first coordinate, the second coordinate, or the third coordinate, right? That was the exercise. So now, how should I conceptualize it? When the very first thing that I'm going to do is to create a data structure that can host the data that I'm going to read once per line, right? So point with index, with index, and this is exactly what I'm doing. I declare, of course, I have a vector. I've already written a class that supports this, that is able to store three floats or in general, a fixed number of floats chosen in compile time. And that was the static vec. This was not required, but I mean, I think it was a nice reuse of what we have already done. So I re-included the file static vec so that I can compose my class by putting trivially an integer and a vector f, which is a vector of float 3 elements. This is going to be what a line of my file is going to contain. Oh, here I started introducing the namespace. We're going to write into the namespace RP, standing from robot program. Okay. All right. Questions on that? I think everything is clear. Of course, I'd also like to, for consistency and for beauty, I'd like to redefine the operators for printing, for loading, and reading one of these data, right? So the reading is done by simply reading the index, reading the value in the first coordinate, second coordinate, third coordinate. The writing is done in the other way, remembering to put the spaces between one token and the next, otherwise everything gets clobbered. Clear? Remember that in order to be able to do ES or cout A greater B greater C, you have to return the modified stream. If you don't do that, you can't progress for the way of resolutions of operators that I have already taught when I was talking about why returning the output stream. And so that's what we're gonna do. Clear? I think that this has no questions. And this tiny little class will allow us to read and write these objects from the stream trivially. Now you understand already that it's quite in the read function, I'm going to use the greater operator. Now let's see what our program was asking. If I recall correctly, load this data from a file and then into a vector, and then prompt the user the sorting method that you want to use, right? Now, remember that if I have 3 sorting strategies, okay, guys, 4, because one is the index, and then I have first, second, and third coordinates, I will have to declare, in theory, 4 function objects, one to pass to the sort. Remember that the sort takes as input as template argument in general, or a hidden template argument, an instance of a sorting method, right? And we have to construct a sorting method that is able to compare, for instance, for the indices. So a sorting method, not sorting method, a comparison operator. And so it's going to be a function object that takes a point and another point, which are the structs that we declared before. Observe that I pass them as const reference because the comparison shouldn't modify the data that I'm giving in. Okay, it's a const method because it doesn't modify the calling object. And all I do is return A index and B index. Of course, I will also use a define at the beginning of the story, a define point with index vector where I define the type point vector of point with indices, right? And this is the first comparison operator. Then there is another thing that I could do. I could either declare 3 different comparison methods for the X, Y, and Z coordinate, or declare only one, a generic comparison operator, at which on construction, I tell which coordinate is gonna be checking, okay? So when I construct, I might define in order to resolve X, Y, Z, what is X? X is the first coordinate, so coordinate in position 0. Y is the coordinate in position 1, and Z is the coordinate in position 3, right? In position 2. So if I could make it a little bit more compact, my program, by declaring a function object, which I call compare coordinate, that has one variable, which is the coordinate, the index of the coordinate that I want to compare, and then on construction, I just do the comparison on that, right? Once I have constructed this object, it will remember which coordinate I casted it to carry on the comparison, and then the comparison will be just that, like take the value. Remember, point with index, how point with index was made. It had two fields, one field which was the index, and the other field which was the value. The value is a member of the struct point with index, and so in order to act, and the value was a vec3f, was elements could be accessed with the method at. As a consequence, if I want to access to the method at of the member called value in a point, I will have to do point.value.at and the element that I'm interested in. So in this case, we extract the value of the coordinate in position coordinate of the first item, and we're going to do the same for the second, and we're going to, return the result of the comparison. Okay. So what is the message? Like that, if you declare function objects, you can also declare variables inside the function objects. They can't be just like, they can have some sort of state inside. It's not forbidden to do so. Okay. And if you can write less code, because remember that the best is to write less code, you could do that. Now, a small caveat, this code is less efficient than another variant of code, which would be the static variant. I could write something like that, slightly less efficient. What I've done is to basically take a parameter that before I was passing it as if it was in the constructor. Sorry, this I delete. You can also delete the constructor because I don't need it anymore. What am I doing here? Basically, I'm saying, okay, declare a class and call it compare coordinate. And one template parameter, which is a constant at compile time, will be called core, right? So inside here, I have core, it's fine. Once I want to declare, for instance, a comparison operator for the first, for the coordinate number 0, I will have to say comp of 0, right? And this is gonna be statically instantiated. And this code is more efficient than the other one because it doesn't need to read into the object which coordinate. Oh, every time you do a comparison, it says, oh, what is my coordinate? Oh, it's core. Let's take it. Let's call the indexing and so on. This code here, if passed to the sort, becomes more efficient because you save some operations. Because you know at compile time, for each instance, which coordinate you have to compare. Okay, guys? That clear? Now we have seen how it's easy to pass from non-template to template version. What you lose is that the possibility at runtime to change in the coordinate. If the coordinate would be a variable, then you can pass a variable to a template. You have to pass a constant to a template. You can't do this. You can't do this. This doesn't work because you don't know at compile time what's the value of I. Okay, this was a small digression. Shall we take this or the other one? Which one do we want? Like, let's comment this. Boom. Right? Okay. Anyway, let's go with the original version and then we can also try the other one. Of course, in order to appreciate, this program is very small. So in order to appreciate, I would have to load an immense number of elements in order to appreciate the difference. All right, let's proceed. We have, at the end of the story, we have declared the class, which is able to store our data fields. We have declared the container of that class in the form of a vector, and then we had defined two kinds of comparison operators. One comparison operator that compares the index, and one comparison operator which is parameterized by the coordinate in a way or in another, that compares the coordinate x, y, or z depending on a number which we have passed. You could also have done it, and probably that's what you have done. You have probably written 3 different compare coordinates. This is version number 1, or you have written one single compare function that takes different arguments. I don't know what was your solution, but this is fine, right? Now let's proceed. What do we expect to do? Well, we check that we have at least 2 arguments. We read the stream. Oh, this is cool because I'm reusing the greater operator that I have defined before when I was declaring the class point with index. So I take the stream and I say read my point with index p from the stream using the greater, because remember that I told the system how to read a point with index. Okay, and thanks to the overloading, I just do this elegantly over there. And then same story as before, I check whether the stream is still good, because I might have reached the end of the files. In this case, I don't want to push it back. If the stream is good, then I push back the point that I just read. Clear? And then I print this amusing message. I loaded the 5 points. Okay, and then let's create, and then we would like to enter in interactive mode, in abuse. But entering in interactive mode, this is my solution. You could also have done it by command line. And so like we have to enter in an endless loop that will stop when the variable run terminates. And then you just like print a message that tells you how you have to sort the point. 1 is the index, 2 is the x, 3 is the y, and 4 is the z. Or we can also be more explicit. We can write I, x, y, z, just like to be more the index x, y, or z, just to be more elegant. So like what we do is we print this message, we declare a character, because in order to read a character, you have to declare a character, which we call it S selection. We read the character from where? Oh, this is an example on how to read from the equivalent of scanf in C. How do I read from the keyboard? With Cin. The keyboard is a stream as any other. I can just like do Cin and read the character. Okay, and then I check the character with this switch construct. So this is a clear multi-selection. And then if you press I, then you sort by index. I call the sort from the beginning to the end, and I call as comparison operator, I pass it an instance of the, this is explicit calling of the constructor. So I just create an object and I pass it over there of compare index. The other one will be a compare coordinate of 0, compare coordinate of 1, or compare coordinate of 2, depending on the result. Is that clear? And then by default, you say if you don't press any of these keys, run equals false, destroy, blast the system, and so on. Okay, because that will set run to false. We'll do another loop, and then at the next round, the program will be terminated. And then if you hit a key, then you say you print the points. These points have been sorted in the container, and then you have. All right. Okay, let's compile this version, and then let's compile also the version with the template. Point multi-sort, test data, and then is point multi-sort data. Okay, it loaded 100 points, I trust it. Let's sort them by index. They are already sorted by index, but E. And then we see that the points are sorted by index. I'm happy. Then it asks me again, because it re-enters in the loop. How do you want to sort them? And now I feel like I want to sort them in the X. I type X, enter. And then you can see that they are sorted by ascending X coordinates. Right? Like, how do you want to sort them? By Y. And then you see that they are sorted by Y ascending coordinates. Right? Okay? Clear? And then I hope you trust me if I say that I could sort them also by Z. Right, something makes sense. All right, then let's move on. Oh, I promised you that I would test the other version of compare. How do I have to declare it? I'll comment region. Now probably I will have some compilation error, but no, not really. I don't feel like. Here, I will have to say compare coordinate underscore. Why underscore? Because I called it underscore. Or let me plus this. Nah. Otherwise you don't find it this way. Compare. You see that compare coordinate template. Bello. Let's call it this way, underscore, just to remember that it's a template. And then we go down, compare coordinate template of what? Of 0. Of 1. Spectacular to work on this machine with the touchpad disabled. Yes. Oh, ready compiled? No. Compile, build. Am I in the right folder? I told you that there will be an error, but where am I compiling? So what it's saying me, expected expression before open token. I understand. Compare coordinate template of 0. Are you right? I'm just declaring a type. This way I'm calling the constructor. Because it requires the brackets to say create the object. Okay. Let's see what was the point. Now we're calling the other one. Let's sort by index, works. By X, works. By Y, works. By Z, works. Clear? So we have seen also how to migrate somehow to a template version of something. Okay, of course, you don't have to do it, but you can do it if you need it, if you need performance. All right, hope this exercise is clear. Let me go to the next. If you have questions, also those at home, please emit sounds containing possibly sentences.
Professor.
Eccolo. Yes, tell me.
Can you, okay, I have a question. In the slides, when we use the sort with the predicate, we removed the brackets, but so we didn't try the code. But now that you put the brackets, are they needed or just it was an error in the slides? There was
an error in the slides that will be fixed. I mean,
okay, so in order to call the predicate,
in general, the compile this should be enough. The point is that the compiler is not smart enough to understand that we're calling the constructor and takes it as a type. And if you do the bracket, you tell him, hey, I'm calling the constructor.
Oh, okay.
So it should work. Send into the specification because, but if you tell it, the bracket means please create an instance of this thing here. Because we are expecting an expression. Look at this. The sort infers out. Oh, we could also do something. If you do this. Oh, CPP references only. No, it's a good one. If you do this, look at the definition of sort. Okay. The definition of sort that we are using, the template definition, contains random iterator and compare. Here, like this is the definition of sort inside the STR. If you do you see big enough?
Yes, it was perfect always before.
Okay.
Also before.
Okay, very good. Now, if we're calling this, basically, once we call the function sort, it looks at this type and it says, oh, this is this argument. Looks at this time and it says it should be equal to this argument. It looks at this type and it should be equal to this. So now, here it expects an instance of an object of type compare. Okay, but this is the meaning. Okay, if you write just compare and basta, presumably in the new C++ standard, is not, you're not declaring an object, you're declaring a type.
Okay, so with the brackets we are creating the object.
Fine.
Okay, okay.
It complained that it's not an expression. I said, okay, now I make it an expression by putting these two things over. And then just, yeah, that's fine. All right, did I answer you?
Yeah, yes.
All right.
Perfect. Thank you.
You're welcome. All right, here we go. Then let's move to the, what was the third one? The binary tree. So to this extent, let me open the old binary tree in template version, that is where we are starting. And I will start from that. Or I can also copy it. Was in 03 CPP templates, 01 binary tree template. That was our binary tree, if I'm not wrong. The old one that we have seen. You remember that we were using the left and the right explicit pointers, right? Let's read what the tree was. We said, oh, that's going to be a template class. So a class which is called tree node underscore. This tree node will have a member, or will have a dependency on a type which we call t underscore. But inside the class, we're going to call this type t underscore that you pass when you declare the template value type, so that we know what it is. And then, given that it's quite annoying to instantiate an object like to call tree node of passing the arguments, we will straightforwardly define a type def that says inside the tree node the type of the tree node itself in template version. So say, oh, if from a tree node I call this type, I mean a tree node which is constructed with the type t. I could write here t for clarity, right? And with a function compare. So I mean really my own type, right? Clear? Why do you need it? Because otherwise, every time I'm referring to a type of myself, I will have to write that large soup. But I could avoid it. Let me revert to the original system. All right. Then we have to declare an object of class compare, right? Which is static. We have seen it last time. And of course, one node of the tree will contain a value and will contain a pointer to the left and to the right, sub3 for the comparison. If you remember that. Do you? All right. And then, okay, the usual constructor, destructors, and insert, and so on and so forth, right? Notably, we had the destructor of the tree. And the destructor is this function that's called when the tree is deallocated. And then, given that the tree contains dynamic structures, to every new, a delete should correspond. And so once you destroy a tree, besides destroying the node itself, you have to destroy the left subtree and the right subtree if they do exist. And that's what the constructor does, the destructor does. All right. This was our old tree version. Now, if we would use the unique pointers, for instance, we wouldn't presumably need to manage any more the memory, because after the first new, once you assign to a smart pointer the memory area, the smart pointer has to manage it for you. So you will never do a delete. Okay? So what could we do? Let me put them side to side. Okay, of course, I'm using the yeah, that's this evil. I will now minimize it, optimize it. Of course, I'm using one more bit of STL, which is the smart pointers, which are defined in the header memory. So this is the old version, this is the new version. The template arguments are exactly the same, because I only have to modify the things. What interesting, what I'm, oh, share pointer, not unique pointer. Like I wanted to be less efficient, but let's say, instead of using the row pointer, like this, I'm gonna use it, define a new type. I call it pointer type, of course, it's 3-node pointer type. And this object here is a shared pointer of a 3-node of this type. Okay, so we define a type, say, oh, there is a smart pointer. It's not a this type star, but there is a smart pointer of the type shared constructed on an object of this type. Clear? Good. And of course, here I had left, here I had right, here I have left and right. But they are both pointer types. Then the rest is symmetric, right? Oh, the insert is interesting. The insert, before it was returning a pointer, right, on success, or on if it had created a new object, and now the insert can't return a pointer, has to return a smart pointer. Okay, you remember, guys? All right. Everything is symmetric. The only difference is in this line over here. This line, before we were saying, okay, if the comparison between the value stored in the tree and the value passed as argument tells me that the passed value is smaller than the value of the node in the tree, and you do not have a left subtree, then you have to create a left subtree by putting in its value this element here passed before, and then you have to return the created left subtree. In the right version, we have to assign to the left element of my node exactly what we were assigning before. Only that we are saying it can't be a pointer straight away. It should be a smart pointer. So construct once a new smart pointer on this pointer created here. Remember that this is an expression that returns the pointer on a newly allocated memory area on which the constructor of the object is called. Right, guys? Clear? Very good. Now, this is a thing, and then out of it, you invoke the constructor of the smart pointer that takes as input the memory area to be managed. It is an error to do something like that. Oh. It is an error to create a pointer, no, a memory area, having this memory area, and then constructing on it two independent smart pointers. Because in this case, the same memory area will be managed by two independent control blocks. And so if you blast one, the other one doesn't know that the previous one has been destroyed, and then this will crash your code. Because when you exit this scope, for instance, it says, oh, this is the thing that has been created. Then here I have two variables, SP1 and SP2. SP1 is destroyed, fine, when you exit this scope, for instance, right? SP1 is destroyed, so I can call the destructor, which will deallocate the memory area P. Then it says, oh, also SP2 is vanished. And then it calls again the destructor of P that deletes once again the same memory area. So once you use smart pointer, assign them only at the beginning on creation, and then copy them and do stuff you want. All right? There must be only one time when you create memory and you assign it to the smart pointer. All right, I can delete this digression. All right, then the rest is basically the same that we have found in the other part of the tree. The print is exactly the same. What's missing between here and here? The distractor. There's no more distractor, because the smart pointer, being a member of the class, when the class is destroyed, also the destructor of all members in the class is called. And so the once you destroy an element of type 3 node, you're gonna destroy, you're gonna call the destructors of all the members, including the member left and the member right, which are smart pointers, which in turn will call the destructor of the contained trees and so on and so forth. Right? So a program that uses this business is basically, let's see, the equivalent. So this was the old version, 3 node int of root. I could also make it perfectly symmetric, but here I use here. So this is the previous version, and this is the new version. Here I did really the butcher, because I created the first object on the stack and all other objects on the heap, right? All the contained thing. I could make these two programs symmetric if you want. Shall I make them symmetric? I made them symmetric. They are the same thing. Same interface. Why? This is the old test example. This is the new test example. Nothing has changed. Okay. I have marked it. No. I have the same out. Of course, I could do variants of this. So this is in binary tree, and this is in source. This is our new version. I could do variants of it. I could explicitly use the fact that the tree is a smart pointer, and so I will have to say here, define the object 3 node on integers, and then here define the variable pointer type nested template of 3 node int. We are accessing the using pointer type of the 3 node. You remember what we have done before? We can access the member class of a class with the member type of a type with a column operator. So this will resolve in binary tree template test yeah, I have to pick out the right one. We are accessing this using over here. No, we're saying 3 node int. It's going to be a 3 node, and then there was the default compare, which was the standard less, and we are accessing a shared pointer of 3 node int. Okay, declare a 3 node int, and we have to create a shared pointer which we call root. Once we create a shared pointer, we can assign it a value, so new 3 node int of 0, and then we manipulate it. All right. Of course, the 3 node will be destroyed at the very end, right? Automatically. So there will be 0 memory leak. If I will run this piece of software in Valgrind, I will see I do not have memory leak. Let me compile. Not cooperative, I think. Binary tree template test. Yes, and Valgrind. For those that do not know what is Valgrind, Valgrind is a program that inspects the memory of the program that it is running, and then it tells you whether that you did mistakes or errors with the memory. And this is what you always want to see once you run Valgrind. 0 errors from 0 context. If there would be a memory leak, then Valgrind will say, you have unallocated stuff. You have not deallocated all the stuff. All right, so let's go to the difficult exercise. If you have questions, I'm gonna take them. Box at home. You in the class, is it all clear? Or reasonably clear? Of course, you have to do it yourself, like in order to. Questions? Fine. All right. Now let's go to the difficult one. In order to the difficult one, I will stop for a second the sharing and I will start moving, shaking my hands. All right. Now, what was the third exercise asking? It was asking basically that I give you a range in a container. A range which is characterized by a begin and by an end, right? You know, a portion of a vector, a portion of a list, or whatever it is. Of course, you need to know that if you do increment the begin or the start, sooner or later you will match the end. Makes sense. It's a reasonable assumption, right? I give you a range. Now, and also I give you a predicate. So what is a predicate? Predicate is a function that either returns a Boolean that can be true or false. Function of what? Function of the item contained into the set, the iterator, basically. If it's a vector of integer, a range on a vector of integer, the item is an integer. An example of predicate would be, is it odd or is it even? Or is it divisible by 3? It's another predicate. Something which is on integers, right? All right. Now, from the template point of view, let's forget for a second about the template machinery and let's think how would you solve this problem on a simple instance of the case. For instance, I give you two indices of a vector, and I'd like you to a function or something that it's a statement that it's either true or false, and I'd like you to put all the elements for which in this range for which the predicate is true at the beginning, and all the elements for which and all the remaining ones at the end, right? So you have to go further and then do a set of exchanges, doesn't matter the order, in a way that at the end you are ensured that all the true ones are in front and all the false ones are at the back. Agreed? This is what I'm asking. So how would you proceed? Well, if they were integers, I would put an integer at the beginning, index, an integer at the end, no? And then I would do the following. I pick up the first element and I compare it with the last element, right? I verify the predicate of the element pointed by the beginning, by this element over here, right? Verify the predicate. If this element is true, so it's okay. It means that this element can stay where it is. So I increment it by 1. Agreed? If this element is not true, I leave the first in the same position, right? Is it fine? And I take the last element of my set and I move it to the first position. Do a swap. So I exchange this element. If it's not true, this means that it should go at the end, right? So basically I exchange the element pointed by the beginning with the element pointed by the end, because I'm making no error in taking this for which the predicate is false and putting it at the end. All right? At this point, by doing this operation, this means that the end is full in this point. And so I decrement the end by 1. Agreed? And then the second step, I compare still the first element, the current element, and then if not, I just like do the same thing. So, okay, so the loop would be, look at the current element. If the predicate is true, advance the begin. If this predicate is false, swap the begin and the end, and decrement the end. All right? At the end of this process, you will have had all the first element, part of the vector fine, the range fine, and all the last where you moved the elements for which the predicate was false. Do you agree that this process works? All right. Now, if you do so, when do you have to stop? When the begin and the end are the same. Okay? That's the mechanism. That's how I would design this. Let's call it algorithm, something rather straightforward. Or this is an operation that you would do, like also to describe to some person which is not the smartest how to implement this thing. Say, look, if button on, then move element to back, leave element where is and move end. If button, right, something like that. All right, very good. So what? Let's see how it how we could do this. How did I call it? Split. Boom. So let's design the interface. It's super commented. The interface of this function will have template arguments because I said let's generate generic code. The template arguments will be the type of the iterator, because that's one of the things that one of the types that are involved here. And the other type will be the type of the predicate, because it's going to be a function object. Okay, this is the template arguments. At this point, I should forget completely that they are template. I should just like reason is as if they were just names of types inside. And then I forget about this thing away. Then
you can't see the screen, Professor.
Sorry. Right. Thank you. Now I have to figure out how to share the screen. Oh, I have 6 elements in the 6 words in the chat. This work as Python. I don't know Python. Sorry, Marco, I don't know Python at all. I mean, I'm firmly convinced. Sooner or later, I will have to learn it, but something that I can't. All right. Okay, but let's design our template. You know, I will have a begin, I will have an end, right? And I will have a predicate type. These will be the arguments that I will pass to the function. In addition, I would also return to the user the element in which the begin and the end were matching. So the separator between the first half, the first part, and the second part, because this is another relevant information that I might want to. That clear? All right. Now I have iterators. Now let me like write poems. Now just do it from scratch. The first question that you ask yourself is what we could do would be, assuming that the iterators behave with star, that the reference we could do, if iterators would support it, iterator type, begin upper. Let's call them lower and upper, and this will be our thing. So while this will be the 2 extremas that they should meet, right? While lower smaller than upper, we could say if predicate is a function object, predicate of what? Of the current element, star lower. what should we do? We should increment lower. Otherwise, what should we do? We should swap lower the contents of lower and upper, right? And then decrement upper. If they were indices, it would work, correct? Now, in order to swap the elements, the naive version would be to change two elements, to exchange two variables. The naive version would be to declare a variable as an appoggio, as a placeholder to do the exchange. The question is like, now here, I'm in a template, in a generic method. So I should be able to declare a variable of the type contained in the iterator. Now, if you look at the documentation of the STL, you figure out that the iterator defines inside the using, which is value type, that is the type that the iterator gets on creation. So iterator type, if you have an iterator on a vector of integers, this iterator type, column, value type, will be an integer. If you have an iterator on a vector of floats, iterator type, the nested type value. Con lezione non posso, ciao. Vediamo dopo. All right, guys. I have to declare a variable. What using value type iterator type. Okay, this is the nested type inside the iterator. That clear? How do you know it? Type of no. Oh, how to retrieve the okay, this is the answer. I hate cookies. You will live with that because I don't want to accept cookies. But the answer was here. See this? Or you? No. Yes, I accept all the cookies you want from. Right? This was the answer. Type name as the iterator, iter. This is the way. Okay, or you do as I say, you just like say iter value type, much better. This is the new version. We are in CP 11, 14, 17. Iterator, column, value type. Okay, because iterator is the type of the iterator. Right? All right, and then we'll have to say you agree with me? I'm just exchanging the elements. With star lower, I'm accessing, yes? Ah, right. Your colleague says out, yes, sorry, was a mistake, right? That's what I would write. Now, and that would be beautiful, right? But that's one problem that, no, the other thing that I need to do is minus upper. Okay, because I have to decrement. I just like copied this element that for which the predicate is false at the end, right? At this point, the end is full, and I have to go back. Okay, all right. That's one problem, that the iterators, they do not support the minus. So you can move forward, but you can't move backward. Okay, the iterators of the STL. So how to resolve this problem? If you look at the documentation, out of an iterator, you can construct another type, which is called, yes, the reverse iterator. Okay, it's a, what is it? It's an iterator that if incremented, it moves backward. So our idea is like that: we take the beginning, take the end, we construct a reverse iterator from the end, which each time it's incremented moves backward, and then each time we have to do the conversion, we will have to convert back each time we have to check this business over here, this comparison, we'll have to figure out whether the lower and whether we'll have to take the end, convert it to the type of the front, and carry on the comparison. So now I hope that this code here becomes clear. Well, of course, I just take value type for cosmesis, even if I don't need it. I have variables which are unused here. Oh, no, they're not unused. All right, I take a value type just because I like it. I start from an iterator lower. I use auto because this basically say create an iterator type, assign to lower the result. So lower is a variable, was type is equal to the type of the expression on the right. The type of the expression on the right is begin, which is of type iterator type. Okay. Then upper, the other end, and I will call browsing in the documentation that is std make reverse iterator of end. End is a forward iterator. To make a reverse iterator, you figure out that there is this function to be called. Of course, this was different. Right. Then, if I give you a reverse iterator, how do you compare it with a forward iterator if they are two different types? You have to access to the inner forward iterator, which is obtained by the base method of the reverse iterator. All right. Then, like here for cosmesis, I just declared two references. These are two references. If you write in a references, you write in the corresponding memory area. I call it v lower, and I take the lower part. I take v upper, which is the lower thing. It's just for cosmesis, okay? The compiler optimizes everything out. Okay, clear? I could blast it if this is disturbing you. Start lower, and start up. Right? And also in this way, I also don't need the value type. But yeah. All right. Then I increment lower. And the other case, before I was decrementing the upper, but the upper now became a reverse iterator. So in order to move backwards, I have to increment. Okay. And then at the very end, I will return the midpoint, which is where the upper stopped. All right. I mean, now if I would delete the comments from here, and I will do, just to have an idea on how compact it can be. That's all. This is the amount of code that you have written that consists in the solution of this test. Right? In terms of code, and in terms of assembly, it will be more or less, no, we are there, right? Okay, now compile. But I didn't expect that. To test it, splitter test. Yeah. All right. Splitter test. Here I just copied it entirely. What an ugly person. Right? Sorry. I just include the header. Hopefully that now I'm opening the main file. Probably now it will not compile. file, file. No, it won't. So now, using namespace robot programming, because we started putting our code into the robot programming business, and then you remember that we have defined a class point with index. Now we can easily put the point with index into a list by declaring a standard list of point with index, which was the class of before. It's basically the same. And then let's define a predicate that we call it odd first. So the numbers that are odd, for the numbers that are odd, the predicate is true. Okay, or is odd, should be. Right? And then what we want to do is to load the points and then to put at the beginning or to run our split routine on a range which goes from the begin to the end of the points, and calling the predicate odd first that will put us 1, 3, 5, all the points with index odd at the beginning and all the points with index even at the end, right? This is a simplistic thing that you could do. Or is negative, is positive, like you can play with it. Oh, notice that this function here, this is how to read, right? It's exactly the same as before, because thanks to the generic programming, we don't have to write any different code. In general, we have to compile different code, but we don't have to write any different code with respect to the vector case. Okay? And whenever we will instantiate a predicate, once we have written our split function that takes a begin, takes an end, that takes a predicate, we don't have to worry about the function or re-implementing it anymore. All we will need to do would be to change the predicate, and everything will be adapted on the spot. Okay? We see, guys? Clear? Well, what I expected to see. Yeah. Point with split the test. And then presumably it requires point, test data, int, no, point not sorted. And that's exactly what we have. The beginning, we have all the points which are odd, and at the end, we have all the points which are even. We did not preserve any sort of ordering or anything, because the requirement was put all for which the predicate is true at the beginning, all for which the predicate is false at the end. I'm not interested in preserving the order or anything like that. I don't want to make any more effort than what I'm doing, right? So like stick to the minimal specification, to the minimum that allows you to solve the problem. All right? Clear? Very good. Okay, this was a difficult exercise, and I buy it. At the same time, it was an exercise that was, I think, rather helpful to introduce new concepts and to show you more or less step by step how to think, let's say, in a generic way. You always think in a specific way when you design an algorithm. And then you try to figure out, hey, what are the elements that now I can abstract from top? And many of these things is getting practical with the documentation and with the standard classes and so on. All right. This stops this part of the lesson. And I think I could directly go on. Do you have questions at home first? In class, are there questions or are you fine? I mean, all right. At home, silence. Okay. All right. So what do we do? What do we do? Do you feel, are you fit for a little bit of another 12 slides of Eigen? Come on. You had a spoiler on the next lesson. All right. Now, let's introduce a rather powerful tool, which is called Eigen, which is more or less a de facto standard in linear algebra with the fixed matrices, vector, and so on. Say, hey, but if Eigen exists, why did you have to make us learning all this template business and so on? As always, because I'd like you to develop the new Eigen when you grow up, or to, I'd like you to become developers of technology, not users. And the real one, not the composing things, mix and match business. And Eigen is surprisingly similar to what we have written. It's a template-based header only. What does it mean? That it doesn't come with a compiled code. The code is generated from the template. So all you need is to include the Eigen headers into your programs to compile. It supports fixed matrices and also dynamic matrices. So fixed objects, fixed and variable size. Of course, if you know the size of your object, it's always better that you use the fixed version. And the basic type is matrix, an Eigen matrix, which you declare this way: matrix type 9 scalar in rows and columns. Where rows and columns can be, if you rows is equal to the constant Eigen column dynamic, which means the word dynamic into the namespace Eigen, which has the value of -1 if you really want to know, then you're saying to the system, hey, this object here has a dynamic number of rows. So you could construct matrices which have dynamic fixed number of columns and dynamic number of rows, or fixed number of rows and dynamic number of columns, or both dynamic or both static, right? If you click or go to this web page, you find all the miracles of Eigen. The thing is that it's very simple to use. Now, now I will show you an example. Now I will show you an example of using Eigen. Normally, I always like to put some music in the game so that I don't have these horrible bracket angular templates around. But it's much easier that I show you a piece of code that uses Eigen. Okay, 05, 06. Oh, no. Basics test file, and now I'll have the fun of the font. Always sounds regular. And then always at one temp. I mean, there must be some. All right. First thing that we do is we include Eigen core, right? Then CD vector, we ignore it. And then we start defining types. Vector 3f, which we call Eigen matrix, is a matrix, a vector of float, tall 3, wide 1. Vector 2f is a matrix, tall 2, so tall 2, wide 1. Matrix 3f 3 by 3, matrix. So it's just type that for me. Okay. Eigen 0, 1, 0, 0, basics test. And here we see Eigen in action. Okay, redefine the thing. We declare matrix 3f command. M1, matrix 3f, M2. M2 set 0, fine. M1, we want to initialize the matrix. If we want to initialize the matrix, Eigen provides this way. You can use the greater operator and then pass a list of comma separated list of the values, and this will be thrown into the matrix. Okay, this is another how this is implemented by overloading the bracket operator and defining. You can also overload the comma, but All right. You can print them. You can assign them. Nice. You can multiply them. Pretty much similar to what we have seen, right? You can extract the column vector from a matrix. You could say, I'm interested in having the column number 0, which is the first column of the matrix. What it's going to be? It's going to be a vector 3f. I could also write here auto, but I could say in this case it's slightly different. It's a return vector type, but I could assign the first column of the matrix to a vector 3f, right? Which is a matrix 3, 1. You can print it, same. You can assign, access the elements, this way. You can do stuff. What happens if we write? This is a matrix, 2 columns, 3 rows, right? How do you know it? Well, knowing myself, this is a type def for a matrix. Knowing myself. Oh yes. This is a type def for a matrix which is tall 2 and wide 3, right? What happens? What do you expect to happen if we uncomment this? We're saying M4. M4 is a matrix which is tall 2 and wide 3, right? So now we are writing in the 4th column, because 0, 1, 2, 3 is the 4th column of a matrix which is large 3. We can't do that. So in theory, this should give us a segmentation fault. Because we are writing, this is the element in position 2, 4 of the matrix. Okay, considering the first element 1, 1. So we are out. I unveil something. Eigen, for efficiency reasons, allocates always a little bit more space than the minimal necessary. So if you are slightly off, sometimes nothing happens. But it's an error. It's a serious error, because you don't know what's going on there. Okay. It supports all the operations that we have seen in our math library, right? And others, right? Including the inversion, the Cholesky decomposition, the eigenvalue decomposition that we're gonna use soon. Okay. So Eigen is nice because we don't have to think much, and it's also highly efficient. Okay. Of course, all the rules apply in not allocating memory when it's not needed, in writing compact expressions. So like, remember that a matrix expression might involve a lot of calculations in the game. So it's good that you write it in compact form. Okay. All right. Do you have questions on that? Or this is kind of straightforward. If I run this business, zero, zero. All right, this is more or less what this program does. All the results of this calculation. The very first thing will be M1. You remember when we assigned to M1 1, 2, 3, 4, 5, 6, 7, 8, 9. M2 set to 0. We printed M2. Video. Okay, so this was print M1. How much is M1? M1 is 1, 2, 3, 4, 5, 6, 7, 8, 9. Not, oh, mamma mia. Because it's, okay. This is M1, this is M2, right? Then the next one, we assign M2 to M1. So M2 is equal to M1, and so on, right? It does what we expect it to do. Okay, guys? Very good. Now let's go on and go a little bit. Let's write a function generic function that loads into a container a variable, so how to say, list or that if you give it a container and you give it a stream, it will infer from the container the type of the elements of the container. And given that the type of the elements of the container, we know that they are going to be vectors. Okay, it determines how many elements are in the vector, and it reads this number of elements from each line of the file. Once it has read this number of elements, takes these elements, creates a new item for the container, and it puts it in the container. Okay, guys? Now, in order to do so, all I need, if I think about it, is to have access to the dimension of the elements in the container. Okay? So to know how big, how many elements is my vector having. Okay? Well, let's see how we could do this. Oh. Oh, those STL, what's the other one? Just close you. No. No. Yes. Now. All right. We want to load points. What do we need to write? A generic function that if we give it a container of Eigen objects, or a container in general, assuming that this container contains Eigen objects, it reads in the string, it reads from the string the Eigen objects into the container. Okay? That clear? So you could declare a list of vector 3f, and then you call this function on a stream, on an input stream or on standard output, and you could tell it load, feed this vector with this. That clear, guys? What I want to do now. The very first thing that I have to ask to the container is, dear container, that you are a type, right? Can you please tell me the type of the object of your items? Is that clear? So we will have a using, and this vector type is the eigenvector type. Sorry, item. Let's call it item type. Okay, much better. More clear now, right? So first I have to figure out. Give me the container, and I have to access the container. What is the type? Because if once I have the type, I can figure out how many elements is this type having, right? But I tell you another thing. Let's do this time. Come on, I was bloated. Then the second thing that I have to figure out is to know for the item how many rows is this item having, assuming that the vector is stored, like it's stored as a matrix in a vertical form, right? So in order to figure out how many rows you have, how can I do? If you remember in the slides, I told you that this template argument becomes inside, is somehow stored in the template, and it becomes inside the template a static variable of the class matrix instantiated as you want. So if you it becomes a special, let's say, constant that you can access by saying rows at compile time. Item type will be the vector. The vector, the rows at compile time of the type of the vector is a constant that depends on the class, because it's a template, will be the dimension. Okay. Once I know the dimension, I can straightforwardly read one after the next all the elements from the stream, bam, 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 into my element of type item type that I extracted from the container. Then the usual, if the stream is good, blah, blah, blah. And then if everything is fine, you take the destination and you push back to it. Understood? Very good. And this is for writing. For reading, won't be much different, right? So this is for reading, sorry. And this is for writing, which isn't much different. The same technique. And the good thing is that this way you can have code that reads for statically compiled things on arbitrary containers, all sort of points with every sort of dimensions. But it doesn't work with the dynamic size. To make it working with the dynamic size, one could straightforwardly, and no, you can't, because you don't know dynamically how many elements the thing has. So you'll have to put a terminator at the end of the row, or you would have to read all the elements one after the other in a vector, in a dynamic structure, and then instantiate a dynamic matrix with that variable number of elements. Okay, because if you don't know how big it is, when do you stop reading a line? You could stop reading a line at the end of line. But if you stop to read the line at the end of line, you have to store somehow the values up until the end of line. Then once you have it, you can create a matrix with that number of elements dynamic. Is that clear? All right. Let's continue with Eigen, and then I think I'll have to, and I think I'll have to stop here because there's people waiting for the lesson. We have still a few minutes for questions because I can't in 4 minutes I don't manage to continue the lesson. Like I'd rather prefer to respond to the questions now, or yeah, or I can kind of boost it a bit, but I don't know whether it's a good idea. So if your questions talk, otherwise I'll stop the recording and I'll say YOLO. Yeah, my recording. Ah, yes. Okay, I'm stopping the recording.